on to the polynomials. So as before, we defined a polynomial to be a function p from our base field to the base field. So p is a polynomial if and only if it's written as a constant plus a constant times z plus constant times z squared, and so on, up to some am z to the m. Where these constants ak are elements of the field, and m is 0 or 1 or some larger integer. Okay, and so notice that in the last video we saw that if you have z plus w and you take its conjugate, or if you have z times w and you take its conjugate, then it's the same thing as if you took the conjugates first and then did the arithmetic operation, right? And so this has consequences for polynomials, which are basically just sums and products, right? So if we have a polynomial and we take its conjugate, then this looks like, see, so we've got sum ak z to the k conjugate, and then by the first property with sums, we can take that inside the summation, ak zk conjugate. And then by the second property, we can split the products. So this is ak conjugate times z conjugate to the k power. So if all of the ak's happen to be real numbers, then this is going to be equal to ak z bar to the k. And that, if you stare at it for half a second, you realize is just p of z bar, right? So now, that last part right here, that last part right there is just in the case when the coefficients are real. But that happens often enough that it's worthy of note. So let's see. So we have proposition 4.7, which says that if p of 0 is equal to 0, sorry, if p of z is equal to 0 for all z, then that can only be the case that all the coefficients are equal to 0. And I'm not going to write down the proof in any detail, but just notice that this is, here, I'll write this as a comment. This is equivalent to saying that 1 z squared da 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 is linearly independent. So if you write down what it means for this to be linearly independent in terms of a dependence relation, then setting it equal to 0 gives you immediately both sides of that proposition. Or, I mean, gives you that proposition, rather. So then we say that lambda is a 0 or root of a polynomial p if and only if it, when you plug it in, so when you substitute its value in for the variable z, you get 0. And the key idea for these which is proposition 415, is that if you've got a polynomial in the complex variable z, but it has real coefficients. So yeah, let me just clarify here. So this right here means z can be in C, but the AKs are going to be in R. So then, if you have a root, its conjugate is a root. So roots come in complex conjugate pairs. And the proof of this we actually already gave. If you look at P of z equals 0 and you conjugate both sides of this equation, then actually here, let's take those off and we'll just say if we conjugate then this is exactly the same thing as on the left, P of z conjugate, and then on the right, the conjugate of 0 is equal to 0 because 0 is a real number.